The cosmos is silent, ancient, and almost entirely empty. Yet here we are. The question of where life came from is the greatest mystery hanging over our existence. This journey explores 30 of the most mind-bending theories for the universe's very first living organisms. By the end, you will see our own origins in a completely new light, from stardust to something stranger than fiction. We will travel from the deep ocean floor to the quantum vacuum, and even confront the possibility that our entire reality is a carefully crafted garden. How many times could life have sparked into being, and what does the very first organism tell us about our place in the cosmos? What feels like the most alien possibility to you? Our story begins not in a warm tidal pool, but in the frozen, airless void between the stars. The first theory suggests we are all cosmic immigrants. This is the idea of Panspermia, the notion that life's building blocks, or even life itself, was delivered to Earth from somewhere else in the universe. Imagine our young planet, still cooling and bombarded from all sides. Among the countless asteroids and comets that pummeled the surface, some may have carried a precious cargo. They were not just balls of ice and rock, they were seeds. The logic is compelling. We know space is filled with complex organic molecules, the very ingredients needed for life. The Murchison meteorite that fell in Australia in 1969 contained over 90 different amino acids, the same compounds that form the proteins in your body. It proved that the chemistry of life is written in the language of the cosmos. But could living organisms survive such a journey? Enter the tardigrade, a microscopic creature often called the water bear. These incredible animals can withstand conditions that would instantly kill almost anything else. They can be frozen to near absolute zero, boiled, crushed under immense pressure, and even survive the complete vacuum and radiation of outer space for years. If a tardigrade can do it, why not a simpler, more ancient microbe tucked safely inside a protective layer of rock? A comet becomes its own life raft, shielding its passenger from radiation as it sails for millions of years. When it finally crashes into a welcoming world like Earth, the passenger awakens. In this view, life did not begin here. Earth was merely the fertile soil where a cosmic seed, planted billions of years ago, finally sprouted. It transforms our search for origins into a galactic detective story. If life can travel between worlds, then it may be far more common in the universe than we ever dared to hope. We are not a solitary accident, but part of a vast, interconnected family tree whose roots stretch across the light years. But what if that seeding was not a random act of cosmic gardening, but a deliberate one? This leads us to a theory that pushes the boundary between science and science fiction, directed Panspermia. The concept is simple and startling. An intelligent, advanced civilization, perhaps facing their own world's end, deliberately sent capsules containing microbial life to new, promising planets. They did not send probes or messages, they sent the very blueprint for existence itself. This idea was seriously proposed by none other than Francis Crick, who co-discovered the structure of DNA, and chemist Leslie Orgel. These were not fringe thinkers, but Nobel laureates who looked at the immense complexity of even the simplest life and wondered if its origin was too statistically improbable to have happened so quickly on Earth alone. They suggested that a technological society elsewhere could have aimed microbial payloads at star systems with young, habitable worlds. Think of it not as an invasion, but as a legacy. Their motivations could be as varied as our own. Perhaps it was a grand biological experiment to see how life would evolve under different cosmic conditions. Or maybe it was an act of pure preservation, a way to ensure that the flame of life, once kindled in their corner of the galaxy, would not be snuffed out by a supernova or some other catastrophe. In this scenario, Earth was not just lucky soil, it was a chosen plot in a galactic arc program. Every living thing on this planet, from the tallest tree to the smallest bacterium, would then be a descendant of that intentional shipment. It reframes our entire existence. Our drive to explore, to spread, to ensure survival might not be a unique human trait, but an echo of a billion-year-old imperative written into life by its original gardeners. The search for our origins becomes a search for our cosmic parents, and if they did it for us, could we, one day, feel compelled to do the same for another young, barren world? Yet the possibility of a cosmic origin forces us to look at our own planet with fresh eyes. If life did begin here, it needed a birthplace, and the classic image of a sunlit tide pool may be completely wrong. The third theory dives into the deepest, darkest parts of our oceans, to a world of crushing pressure and scalding heat. This is the deep-sea hydrothermal vent hypothesis. Forget the warm little pond. Picture instead a landscape more alien than anything on the surface. Towering chimneys, some as tall as skyscrapers, rise from the ocean floor, belching out superheated, mineral-rich water from deep within the Earth's crust. These are the vents. The black smokers jet out water darkened with iron and sulfide, creating vast, dark plumes. The white smokers are slightly cooler, releasing water rich in barium, calcium, and silicon, giving them a ghostly, pale appearance. To us, this environment seems utterly hostile. The pressure is hundreds of times greater than at sea level. There is no sunlight whatsoever, and the water can be heated to over 700 degrees Fahrenheit. But within that apparent hostility lies a remarkable opportunity. The porous rock of the vent chimneys acts like a natural, intricate laboratory. They are filled with millions of tiny compartments and channels. As the hot, chemical-laden water from below meets the cold, acidic seawater, it creates steep gradients both in temperature and chemistry. These gradients can provide a steady, reliable source of energy, much like a battery. More importantly, the mineral walls of the chimneys can attract and concentrate simple organic molecules, the building blocks of life, holding them close together long enough to react and form more complex chains. It is a perfect incubator, protected from the violent asteroid impacts that scarred the early Earth's surface. The most compelling evidence for this theory is not a fossil, but what lives there right now. Today, entire ecosystems thrive around these vents, completely independent of the sun's energy. Giant tube worms, strange clams, and swarms of blind shrimp all exist thanks to chemosynthesis, where microbes convert the vent's chemicals like hydrogen sulfide into food. These microbes are the foundation of the entire vent community. Could their ancient ancestors have been the very first organisms, not just living near the vent but born from its chemistry? In this view, life did not timidly emerge in a quiet pool. It roared into existence in the fiery, mineral-rich heart of a planetary forge, powered not by sunlight but by the very heat of the Earth itself. It suggests our most distant ancestor might have been a heat-loving microbe, clinging to a rocky pore in the eternal dark, finding energy in the stone and chemistry in the sea. But if life truly did begin in a place like a hydrothermal vent, it still leaves a monumental question unanswered. How did inert chemistry cross the threshold into something that could grow, change, and most importantly, copy itself? The fourth theory tackles this head-on with a molecule that is both a message and a machine. This is the RNA world hypothesis. Before DNA became the famous blueprint of life, and before proteins became its versatile workforce, there was a simpler, more versatile pioneer. RNA, or ribonucleic acid, is often seen as just a messenger carrying instructions from DNA to build proteins, but it is capable of so much more. RNA has a unique and almost magical duality. It can store genetic information, just like DNA, in the sequence of its building blocks, but unlike DNA, it can also fold into intricate three-dimensional shapes and act as a catalyst, speeding up specific chemical reactions. An RNA molecule could, in theory, be both the instruction manual and the factory that reads it. Imagine a single, remarkable strand floating in a warm, chemical-rich pool. By chance, its shape allows it to attract and stitch together loose building blocks that are floating nearby. It assembles them in a sequence that mirrors its own. In a flash of chemical copying, it creates a complementary strand. And if that new strand can then do the same thing, you have the beginnings of a self-sustaining cycle. You have a molecule that can make copies of itself. This is not just a thought experiment. In laboratories, scientists have created RNA molecules called ribozymes that can do exactly this. They have engineered strands that can catalyze the assembly of their own copies, link pieces of RNA together, and even evolve under selective pressure. These experiments show that the leap from chemistry to a primitive form of evolution is not only possible, it is demonstrable. In the RNA world, life did not begin with a cell. It began with a naked, self-replicating molecule, a tiny chemical engine that, once it started turning, could never be stopped. These first replicators would have been in constant competition for the building blocks around them. The ones that copied faster or more accurately would have come to dominate the primordial soup. Mistakes in copying, mutations, would have introduced variation, and natural selection would have begun its work at the molecular level. It is a breathtakingly simple and elegant idea. The first organism may not have been a cell at all, but a persistent, replicating pattern of information written in a chemical code, dancing on the edge between order and chaos, and slowly learning how to build a world around itself. The replicating molecule is a powerful idea, but it has a critical vulnerability. A naked strand of RNA floating free in an ancient sea is at the mercy of its environment. It can be torn apart by waves, diluted into nothingness, or its precious building blocks can simply drift away. For life to truly take hold, it needed a home. This brings us to a theory that turns our attention from information to architecture, from the message to the house it lives in. This is the lipid world hypothesis. While the RNA world asks what came first, the genetic code, the lipid world asks what came first, the cell itself. Its foundation is a simple, profound fact of chemistry. Certain molecules, called lipids, have a split personality. One end of the lipid loves water, it is hydrophilic. The other end fears it, it is hydrophobic. When you have a bunch of these molecules in water, they do something beautiful and automatic. They arrange themselves to hide their water-fearing tails and expose their water-loving heads. The simplest way to do this is to form a double-layered sheet, a barrier. But if you agitate them, they can do something even more remarkable. They can curl in on themselves and seal into perfect hollow spheres. These are called vesicles, and they are the ghostly ancestors of every cell membrane on Earth. Imagine a primordial tide pool or a vent's mineral pore, rich with these lipid molecules. With every wave, every temperature change, countless tiny bubbles would have spontaneously formed and dissolved. They were not alive, but they were the first closed spaces. Now picture one of these bubbles as it pinches off. Trapped inside its protective lipid shell is a random sample of the surrounding soup, perhaps containing a few amino acids, a strand of RNA, or other organic compounds. Suddenly, the chemistry inside this tiny compartment is isolated. It is a private laboratory, shielded from the infinite dilution of the open ocean. Different vesicles would have contained different chemical mixtures, creating a vast experiment in early Earth chemistry. Some bubbles would have been more stable than others. Vesicles with certain lipid compositions might have lasted longer, or been better at growing by absorbing more lipids from their surroundings and then splitting in two when they got too large. This is where selection enters the picture, not yet based on genes, but on simple physical and chemical stability. A vesicle that could grow and divide more reliably would become more numerous. Now consider a vesicle that, by chance, encapsulated a molecule that could speed up a useful reaction, perhaps helping to strengthen its own membrane or capture energy. That vesicle would have an advantage. It is a tiny chemical feedback loop where the contents benefit the container and the container protects the contents. In this view, the first stirrings of evolution were not about copying information, but about maintaining a stable, self-perpetuating system. The lipid world suggests life began not with a replicator, but with a protector. The bubble came first, creating the necessary space where the chaotic chemistry of the early Earth could become organized, concentrated, and eventually self-sustaining. It is a humbling thought. The very boundary that defines every one of your trillions of cells that separates you from the outside world might be the oldest relic of life's first, fragile attempt to carve out a self from the formless sea. But these protective bubbles, these first private laboratories, needed something to organize the chaos within. They needed a template. The sixth theory suggests that the first template for life was not organic at all, but made of stone. This is the clay crystal hypothesis, a profound idea that connects the very ground beneath our feet to the origin of all living things. Imagine the early Earth, a world of rock and water. In certain places, like the muddy edges of volcanic pools or river deltas, you would find clays. To us, clay is just dirt, but at the microscopic level, it is a marvel of natural engineering. Clay minerals form in thin, stacked sheets with incredibly orderly, repeating patterns, like a vast atomic honeycomb. Their surfaces are charged, attracting and holding onto specific molecules from the surrounding water. The champion of this idea, the scientist A.G. Cairns Smith, proposed something revolutionary. He argued that long before RNA or lipids, these inorganic clay crystals were the first systems capable of something like evolution. Here is how it could have worked. As clays form and grow, they do not simply expand like a blob. They grow by adding new layers in a precise, repetitive pattern. Sometimes during this growth, a defect occurs in the crystal lattice, a tiny misplacement of atoms. When that flawed crystal then serves as a template for new growth, it can copy that defect. In essence, the crystal structure carries information, and it can replicate mistakes and all. Now picture these growing clay crystals in a rich, organic soup. Their charged surfaces would act like a magnet, grabbing amino acids and other building blocks, arranging them into orderly rows along the crystal's own pattern. Over time, these organic molecules might begin to link up, forming chains that mirrored the inorganic template that held them. The clay is not alive, but it is performing a crucial service. It is concentrating and organizing organic chemistry, creating complex patterns where there was only randomness. Eventually, according to the theory, the organic molecules became so complex and so good at their own chemistry that they took over. They became self-sufficient, forming their own replicating systems, perhaps the first RNA strands. At that point, the clay scaffold, having served its purpose, was discarded. Life, in a sense, learned how to copy itself from the rocks and then left its stony cradle behind. This idea elegantly solves a major puzzle of the RNA world. How could something as complex as a self-replicating molecule arise from pure chance in a dilute soup? The clay provides an answer. It offers a pre-existing, non-living system that already knew how to grow, replicate patterns, and evolve in a primitive way. It suggests that the first genetic code was not written in molecules we now consider the essence of life, but in the silent, geometric language of geology. We may not be children of the stars or the deep sea vents alone. We might also be children of the mud, our most ancient heritage etched in the crystalline memory of the earth itself. Yet the idea of a clay template still requires a rich source of organic ingredients. Where did that primordial chemical soup come from in the first place? For decades, the most famous answer came from a simple glass apparatus in a university laboratory. This is the story of the primordial soup brought to life in a single, electrifying experiment. In 1953, a young graduate student named Stanley Miller, working under his advisor Harold Urey, decided to test a bold hypothesis. Could the basic building blocks of life have been cooked up by the natural conditions of the early Earth? They built a device that was both elegant and dramatic. One flask represented the ancient ocean filled with warm water. Another contained a mixture of gases they believed mimicked the early atmosphere: methane, ammonia, and hydrogen. They connected the flasks with glass tubes, and then they introduced the spark of creation, literally. Electrodes sent continuous electrical discharges, simulating the intense lightning storms that would have raged across the young planet. For a week, the miniature world churned and sparked. The water boiled, condensed, and rained back down, circulating the gases through the electric fury. What Miller found when he analyzed the contents was nothing short of revolutionary. The once clear water had turned a murky, reddish-brown. More importantly, it was teeming with organic compounds. The experiment had produced several amino acids, the very molecules that link together to form proteins, the workhorses of every living cell. It was a stunning result. For the first time, someone had taken simple, inorganic ingredients thought to be present on the early Earth, applied a plausible natural energy source, and created the fundamental bricks of life. The news made global headlines, and the image of lightning striking a chemical soup became the iconic picture of life's origins for a generation. It seemed to prove that the leap from non-life to life's ingredients was not only possible, but almost inevitable given the right conditions. The primordial soup was not just a metaphor, it was a recipe that nature could easily follow. Of course, science moves forward, and our understanding of the early Earth has evolved. Many scientists now doubt that the atmosphere was as rich in methane and ammonia as Miller and Urey assumed. Geological evidence suggests it may have been dominated by carbon dioxide and nitrogen, a mix less conducive to the kinds of reactions they observed. The experiment has also been critiqued for being too pristine, protected from the destructive ultraviolet light that would have bathed the planet without an ozone layer. Yet to dismiss the Miller-Urey experiment because of these later critiques is to miss its profound and enduring point. It was a monumental proof of concept. It demonstrated that the complex molecules of life could arise from simple beginnings through ordinary planetary processes. It took the question of life's origin out of the realm of pure philosophy and placed it firmly into the domain of testable experimental science. That glass apparatus did not create life, but it lit a path for all who followed, showing that the universe has a built-in chemistry that leans toward complexity. It told us that the ingredients for us were not magical but mundane, waiting in the air and water of a newborn world, ready to be assembled by the most common force of all, a storm. Yet the Miller-Urey soup, for all its brilliance, was a passive brew. It created the building blocks, but it lacked an engine, a driving force to assemble those blocks into something that could sustain itself. The eighth theory provides exactly that engine, and it is forged from the very rocks of the seafloor. This is the iron-sulfur world, a vision where life began not just near a vent, but as an integral part of its mineral fabric. The central character in this story is a common, fool's gold mineral called pyrite or iron sulfide. The chemist Gunther Wechtershauser proposed a radical shift in perspective. He argued that the first steps toward life were not about replicating molecules in an open soup, but about establishing a primitive metabolism, a way to capture energy and build complexity right on the surface of a crystal. Picture not a black smoker, but a different kind of deep-sea marvel, an alkaline hydrothermal vent. These structures, like the Lost City field in the Atlantic, are formed not by volcanic magma, but by a chemical reaction between seawater and a type of rock called olivine in the Earth's mantle. The water that percolates up is warm, not scalding, and rich in hydrogen. It is also highly alkaline. When this fluid meets the acidic, carbon dioxide-rich ocean water, it creates a natural electrochemical gradient across the porous, rocky walls of the vent. It is a natural battery, and its electrodes are made of metal sulfide minerals. Now, imagine the surface of a freshly formed iron sulfide crystal at such a vent. Its geometric lattice is not inert. It is chemically active with a positively charged surface that can attract and hold negatively charged molecules like carbon dioxide. Hydrogen gas from the vent's fluid provides a stream of electrons. On this mineral stage, a simple but profound reaction can occur. The iron sulfide surface acts as a catalyst, using the energy from the chemical gradient to drive carbon dioxide and hydrogen to react, forming simple organic molecules like acetic acid. This is not a random assembly in a dilute pool. It is a directed, energy-driven production line anchored to a solid surface. In Wechterscheus's vision, this was the first metabolism. A network of chemical reactions powered by the vent's natural chemistry and organized on the scaffolding of the mineral began to build more complex carbon-based compounds. The pyrite surface is not just a catalyst, it is also a home. As organic products accumulated, they could have formed oily films that coated the mineral, eventually creating primitive cell-like compartments directly on the rock face. Life in this scenario began as a chemical film, a living rust on the walls of a submarine geyser. Genetics and replication came later as a way for this successful metabolic network to stabilize and spread. This idea turns the traditional story on its head. Instead of genetics first, it proposes metabolism first. The initial spark was not a molecule copying itself, but a self-sustaining chemical cycle that could draw energy from its environment and use it to grow. It suggests our most ancient ancestor was not a solitary replicator, but a cooperative chemical flow, a pattern of energy and matter that found a way to persist on the face of a stone, fed by the slow, steady breath of the planet itself. The shift from the deep sea to the sunlit surface brings us to a landscape of steam and simmering earth. Theory 9 proposes that life did not need the crushing pressure of the abyss, but found its perfect crucible in the dynamic, ever-changing pools of a volcanic hot spring. These are not the gentle hot tubs of a spa, but the geologically active margins where water meets magma, creating a mosaic of scalding vents, bubbling mud pots, and terraced mineral pools. While deep sea vents offer constant conditions, these terrestrial springs provide something arguably more valuable for the leap from chemistry to biology, a relentless cycle of wet and dry. Picture a small, warm pool on the slopes of an ancient volcano, rich with dissolved minerals and simple organic compounds washed in from the surrounding clay. The sun beats down and the water slowly evaporates, concentrating the soup within to a thick, syrupy consistency. Molecules that once floated far apart are now pressed together, dramatically increasing the chance they will link up and form longer chains. Then a rain shower comes or water from the spring's source overflows, suddenly diluting the pool again. This wet-dry cycle is not a minor detail, it is a powerful chemical engine. In laboratory experiments that simulate these exact conditions, researchers have watched as simple building blocks, like the nucleotides that make up RNA, are driven to form long polymer chains when subjected to repeated hydration and dehydration. The dry phase promotes the chemical bonds that link the units together, while the wet phase allows for rearrangement and new combinations. It is a natural, rhythmic process that coaxes complexity from simplicity. Furthermore, the edges of these pools are often lined with fine clay and volcanic ash. As we learned from the clay crystal hypothesis, these minerals can act as catalysts and templates, holding the emerging molecules in place and guiding their assembly. A hot spring pool becomes a complete, integrated laboratory. It concentrates ingredients, provides thermal energy from below, offers mineral catalysts on its borders, and subjects the entire mixture to the driving pulse of wet and dry cycles. On the early Earth, which was far more volcanically active than today, such environments would have been common, scattered across the first continents like a network of natural experiments. This hypothesis paints a compellingly terrestrial origin story, one where life may have first knitted itself together in the shallow, sun-dappled waters of a geothermal oasis, dancing to the ancient rhythm of rain and evaporation, building its first complex molecules one drop at a time. This idea of a cosmic seed leads to a theory so vast it redefines life's place in reality itself. Cosmic ancestry proposes that life did not begin on Earth or even at a single point in time. Instead, it suggests life is eternal and ubiquitous, a fundamental property of the cosmos as intrinsic as gravity or light. In this view, the universe has always contained life, and life is continually distributed across galaxies through the mechanisms of Panspermia. The question shifts from how life began to how it persists and spreads. Proponents like astronomer Fred Hoyle and astrobiologist Chandra Wickramasinghe argued that the incredible complexity of even the simplest cell points not to a miraculous accident on one world, but to an infinite universe with infinite time for life to have always been here. They saw the interstellar dust clouds not as barren voids, but as cosmic nurseries teeming with organic molecules and perhaps dormant microbes. Every comet, every asteroid, every wisp of cosmic dust becomes a potential carrier. This transforms our understanding completely. There is no first organism because life never had a beginning in the way we conceive it. It is a cycle without a start, as perpetual as the expansion of space. The philosophical implications are staggering. If true, life is not a rare and fragile spark in a dead universe. It is a cosmic constant. We are not the result of a 1 in a trillion chance, but a natural expression of a universe that is inherently biophilic, life-loving. Our existence here is not a solitary miracle, but a local manifestation of a universal condition. This perspective makes the search for extraterrestrial life almost a foregone conclusion. The galaxy is not sprinkled with rare oases of life. It is an interconnected ecosystem on a scale we can barely fathom. Our own planet's history of life becomes just one chapter in an epic that has no first page, a story written not in the rocks of Earth, but in the fabric of the cosmos itself. The eternal cycle of cosmic ancestry suggests life is woven into the universe's fabric, but what if it is stitched together with threads stranger than anything we have described? The 11th theory ventures into a realm where the rules of our everyday reality dissolve, proposing that the spark of life was not just chemical but quantum. This is the frontier of quantum biology, and it asks if the bizarre phenomena that govern subatomic particles could have been midwives at the birth of the very first organism. At the heart of this idea are principles that sound like pure science fiction. Superposition, where a particle exists in multiple states at once until it is observed. Quantum tunneling, where a particle passes through a barrier as if it were not there. Entanglement, where two particles become linked, instantly influencing each other across any distance. These are not just theoretical curiosities. We now know they operate within living systems right now. The process of photosynthesis, which plants use to turn sunlight into energy, appears to use quantum coherence to find the most efficient path for energy transfer. Some birds navigate using a quantum compass in their eyes, sensing Earth's magnetic field through entangled electrons. If nature uses these tricks today, could they have been present at the very beginning, making the impossible leap from chemistry to life not just possible but probable? Imagine a proto-RNA molecule, a candidate for that first replicator, trying to perform the delicate chemical dance of copying itself. A key step might require moving a proton from one atom to another, but the energy barrier is just a little too high for ordinary chemistry to overcome. In the classical world, the reaction fails, but in the quantum world, that proton could simply tunnel through the barrier, appearing on the other side as if by magic, enabling the reaction to proceed. Quantum tunneling could have acted as a hidden shortcut, accelerating the slow, random chemistry of the primordial soup, or consider superposition. A simple biomolecule in a quantum state might have explored multiple chemical configurations simultaneously, effectively testing many potential paths to a successful reaction at once. It would be like a lock trying every possible shape of key at the exact same moment to find the one that fits. This quantum exploration could have dramatically sped up the search for the right molecular arrangements that could sustain and replicate themselves. The most profound speculation involves entanglement. If the first self-sustaining chemical cycles relied on a network of reactions happening in concert, quantum entanglement could have provided a form of instantaneous communication between different parts of the system, coordinating them with perfect synchronicity. This would create a unified, coherent whole from what would otherwise be a collection of separate, inefficient chemical events. In this light, the transition from non-life to life might not have been a slow, grinding climb over a chemical mountain. It could have been a quantum leap where the weird, probabilistic fog of the quantum realm provided the scaffolding for stability to emerge. The first living system might not have been a classical machine, but a quantum melody, a coherent pattern of information and energy that learned to preserve itself. It suggests that life, from its very inception, was not separate from the deepest, most fundamental layer of physical reality. We are not just stardust. We may be a manifestation of the universe's most intimate and mysterious behavior, a persistent vibration in the quantum field that one day learned to call itself alive. The quantum melody of the first life hints at a process, but what if the very definition of life is the problem? The 12th theory confronts this by suggesting the first organism was not an organism at all, but something far stranger. This is the idea of the zombie virus, a term for ancient pre-biological replicators that existed in a gray zone between chemistry and biology. They were not alive by any definition we use today. They did not have cells, they did not metabolize, and they may not have even used DNA or RNA. Yet they possessed the two most critical hallmarks of life: they could replicate and they could evolve. Think of them not as creatures but as persistent chemical echoes. One of the simplest examples is an autocatalytic cycle. This is a set of chemical reactions where the product of one reaction is the catalyst that starts the next, eventually looping back to recreate the starting material. Once such a cycle is kick-started, it becomes self-sustaining, a closed loop of chemical activity that churns on as long as there is fuel. It makes more of itself, not by copying a blueprint, but by perpetuating a process. Another candidate is a clay crystal, as we discussed earlier, growing and copying defects in its lattice. These systems are the ultimate zombies. They are not dead because they are active and changing, but they are not alive because they lack the complexity and independence we associate with a living cell. They exist in that eerie borderland, a chemical purgatory. Their power lies in their simplicity. In the chaotic primordial soup, these stable, self-reinforcing patterns would have had a tremendous advantage. They would have consumed available resources, outcompeting random chemical reactions, and crucially, they were subject to change. A random mineral impurity, a fluctuation in temperature, or a new molecule drifting into the cycle could alter it slightly. If that alteration made the cycle more robust or more efficient at gathering resources, that new version would thrive. This is evolution in its most raw, chemical form, natural selection acting on non-living matter. The zombie replicator theory elegantly bridges the gap. It proposes that life did not suddenly appear in a flash of lightning. It emerged through a gradual series of steps where each stage was just stable enough to persist and evolve into the next. First came persistent chemical patterns, the zombies. Over immense stretches of time, these systems likely became more complex, perhaps incorporating lipids to form protective bubbles, or RNA molecules that could store information about the successful cycle. Eventually, one of these hybrid systems crossed a threshold we can no longer clearly see, becoming what we would definitively call alive. This reframes our search for the first organism. We are not looking for a microscopic cell in the fossil record. We are looking for the ghost of a chemical rhythm, a self-perpetuating reaction that vanished billions of years ago, leaving no trace except for everything that came after. It suggests that the line between life and non-life is not a bright, clear border, but a vast and foggy marshland, and we are the descendants of whatever finally crawled out onto the other side. These persistent chemical echoes, however, needed a rich and constant supply of parts. While our planet offered many potential workshops, the ultimate source for those building blocks may have been far more exotic. The 13th theory takes us back to the depths of space, but with a crucial twist. Comets were not just passive delivery trucks carrying pre-made ingredients. They were dynamic, cosmic factories, actively manufacturing the very molecules of life as they journeyed through the solar system. For decades, we saw comets as dirty snowballs, simple amalgamations of ice and dust. But modern science reveals them to be astonishingly complex chemical reactors. A comet's heart, or nucleus, is a porous, icy body loaded with frozen gases like carbon monoxide and methane, along with dust grains rich in silicates and carbon. For most of its long orbit, this nucleus is frozen solid in the outer solar system, a dormant chemical archive. The magic happens when its elliptical path swings it in toward the sun. As solar radiation heats the surface, the ices don't just melt, they sublimate, turning directly from solid to gas. This outgassing creates the comet's spectacular coma and tail, but it also triggers a frenzy of chemistry in the thin, icy mantle just below the surface. Here, in this active boundary layer, high-energy ultraviolet light and cosmic rays bombard the simple molecules. This radiation provides the power to break molecular bonds and forge new, more complex ones. In laboratory experiments that simulate these exact conditions, scientists have watched as ices containing water, methanol, and ammonia, when irradiated, produce a stunning array of organic compounds, including amino acids and even sugars like ribose, a critical component of RNA. The comet becomes a mobile chemical plant, using the sun's energy to assemble life's precursors as it travels. This isn't just a laboratory prediction. We have gone to a comet and seen it for ourselves. The European Space Agency's Rosetta mission, which spent 2 years orbiting Comet 67P, provided breathtaking confirmation. Its onboard instruments detected a wealth of prebiotic molecules in the comet's coma, including the amino acid glycine and the key element phosphorus. More importantly, Rosetta found that the organic material was often complex and carbon-rich, not just simple chains. The Philander even detected organic polymers on the surface, molecules that could serve as the backbone for more complex structures. This data paints a picture of comets as not merely carriers but prolific producers. Each comet on each pass near the sun could be enriching itself with a new batch of biologically relevant compounds. When such a comet later collided with the young Earth, it didn't just sprinkle a few amino acids into the ocean. It could have delivered a concentrated payload of diverse, complex organics, the products of millions of years of cosmic chemistry. This theory elegantly combines the vast resources of space with the energetic trigger of a star. It suggests the universe is not just stocked with life's ingredients, it is constantly, actively cooking them in countless icy kitchens, sending them inward to worlds like ours, ready to jumpstart the next great experiment. The idea of comets as cosmic factories pushes our search for origins to an even more fundamental birthplace. Before planets, before stars, there exist vast, silent nurseries in the emptiness of space. Theory 14 suggests life's first chapter was written not on a world, but in the profound darkness between them, within the cold heart of an interstellar cloud. These are not empty voids, they are the richest chemical reservoirs in the galaxy, colossal clouds of gas and dust so dense they blot out the light of stars behind them. Within their freezing embrace, temperatures hover just a few degrees above absolute zero, and the primary form of water is not liquid but solid ice, coating every microscopic dust grain like a tiny frosty mantle. To our human senses, this seems like the most sterile environment imaginable, a place where all chemistry must grind to a halt. Yet paradoxically, this deep cold is a key ingredient for creation. It allows fragile molecules to form and survive. When atoms and simple molecules like carbon monoxide, ammonia, and hydrogen float freely in the warmth of space, they bounce off each other too energetically to stick. But on the surface of an icy dust grain in a molecular cloud, they land and stay put. They slide across the ice until they meet another atom, and in the stillness of that deep cold, they bond. Slowly, over millions of years, these grains become tiny chemical laboratories, their icy surfaces accumulating layers of increasingly complex organic goo. But cold alone is not enough to build life's ingredients. These clouds need an energy source, and they have one in abundance: cosmic rays. These are not rays of light, but high-energy particles, protons and atomic nuclei, screaming across the galaxy at nearly the speed of light. They constantly pepper the interstellar clouds, piercing the dust and ice. When a cosmic ray strikes a molecule on a grain of ice, it acts like a microscopic bolt of lightning, delivering a burst of energy that can break apart old bonds and forge exciting new ones. This slow, steady irradiation over astronomical timescales can manufacture molecules of startling complexity. Astronomers using radio telescopes have identified over 200 different molecular species in these clouds, including alcohols, acids, and even a simple sugar called glycolaldehyde. These are the same types of molecules that, delivered to a young planet like Earth, could have been the starter kit for biology. The interstellar cloud hypothesis presents a humbling and grand vision. It means the building blocks of life are not a rare planetary accident, but a universal byproduct of star formation itself. Every new star and its family of planets are born from a cloud already seeded with the precursors of biology. Before our sun even ignited, before the Earth coalesced from a disk of dust, the potential for us was already there, frozen onto a trillion specks of dust drifting in the silent dark. In this view, we are not just children of Earth or the Sun, but descendants of the galaxy's own icy interstellar chemistry, a testament to the fact that even in the deepest voids, the universe is quietly, patiently assembling the pieces of something remarkable. Yet this cosmic distribution of life's ingredients sets the stage for an event of almost unimaginable violence. The interstellar clouds gave us the pieces, but it may have taken a planetary-scale cataclysm to truly assemble them. Theory 15 proposes a dramatic twist on the Panspermia idea, one where life is not just delivered from afar, but blasted off its own cradle and then returned like a cosmic boomerang. This is the planetary collision and receding theory. To understand it, we must travel back over 4 billion years to a time when the solar system was a chaotic shooting gallery. The dominant model for the origin of our moon suggests that a Mars-sized protoplanet, often called Theia, slammed into the young Earth. The impact was apocalyptic, melting the entire surface of our planet and ejecting a colossal amount of vaporized rock and debris into orbit. That debris eventually coalesced to form our moon, but consider the other debris, the countless smaller fragments of rock that were not gravitationally bound to become part of the moon. Many of these were hurled away from Earth entirely, cast out into the solar system. Now, here is the pivotal question. What if life, in its most primitive microbial form, had already begun on Earth before this colossal impact? It is a radical possibility. If simple, hardy microbes existed in the crust or deep underground, they could have been caught in the ejector. Encased within the heart of a rock, shielded from the heat of re-entry into space, a microbe might survive the initial blast. It would then find itself on a new, terrifying journey, a piece of its homeworld now adrift in the void. This rock becomes a life raft on an interstellar scale. For millions of years, it orbits the Sun, a silent tomb or a dormant ark. But orbits are not always stable. Gravitational tugs from other planets can alter its path. Eventually, some of this ejected material could have found its way back, falling to Earth as meteorites millions of years after the original cataclysm. In this scenario, life on Earth would have been delivered by Earth itself. The planet would have effectively reseeded its own surface with its own biological legacy after a period of sterilization. This idea becomes even more compelling when we consider our neighbor, Mars. We know Mars was once warmer and wetter, with conditions potentially suitable for life even earlier than Earth. A large asteroid impact on early Mars could have blasted Martian rocks into space, some of which eventually fell to Earth as meteorites. We have actually found Martian meteorites here on Earth, proving this transfer is possible. If Martian life existed, it could have hitched a ride. This means we might all be descendants of Martian microbes, with life on Earth being a second attempt after a more promising start next door. The planetary collision theory reframes extinction-level events not just as endings, but as potential dispersals. A world-shattering impact would certainly wipe out most surface life, but it could also propel the survivors on a journey across the solar system. Life, in this view, is not a fragile flame easily snuffed out. It is a tenacious spark that can be scattered by the very explosions meant to destroy it, waiting in the deep freeze of space for a chance to ignite again on a new world, or even on its old one, reborn from its own ashes. It suggests that life, once it gains a foothold, might be nearly impossible to eradicate completely from a planetary system, because the universe itself becomes its backup drive. The violence of planetary collisions suggests life is tenacious, but what if its most successful forms are hiding in plain sight? This brings us to a theory that challenges our very ability to see the life around us. It is the concept of a shadow biosphere. We assume all life on Earth shares a common ancestor, that every bacterium, every tree, every human uses the same basic biochemical toolkit. DNA for information, proteins for work, and a specific set of elements like carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Our entire search for life, from the deepest ocean trench to the soil of Mars, is calibrated to detect these signatures. But what if that assumption is blinding us? The shadow biosphere proposes that Earth could host a second genesis, a completely independent tree of life that arose separately and remains undetected because it operates on a different chemical language. Imagine a microbe that does not use phosphorus in its backbone but arsenic, or one that uses a solvent other than water, perhaps liquid methane or ammonia, thriving in environments we consider utterly toxic. These would not be aliens from another world. They would be true aliens here at home, descendants of a genesis event that happened alongside our own, but lost the competition for the prime ecological niches and retreated into the extreme margins. We may have already held them in our hands and discarded them as dead or inert because our tests designed to amplify DNA or detect familiar metabolic products would find nothing. They would be ghosts in the machine of our detection. The implications of finding such a shadow biosphere would be seismic. It would prove that the spark of life is not a one in a trillion fluke, but a common, repeatable event even on a single planet. If life arose independently twice on Earth, then the universe must be absolutely teeming with it. Our own form of biology would become just one possible expression of a universal principle, one flavor of life in a cosmic buffet of possibilities. The search for these hidden neighbors is already underway. Scientists are exploring places like the hypersaline and arsenic-rich waters of Mono Lake in California, or the ultra-acidic drainage from mines, deliberately looking for organisms with weird chemistries. They are developing new tools that look for patterns of complexity and energy use rather than specific molecules. Finding a shadow biosphere would be the most profound discovery in biology since Darwin. It would tell us that life is not a singular miracle, but a natural force as inevitable as crystallization or weather, waiting for any suitable niche to express itself. We would have to rewrite our textbooks not just about life on Earth, but about life everywhere. The universe would transform from a mostly dead expanse into a garden of infinite biological variation, and we would have to accept that we have been sharing our home for billions of years with a secret we were not equipped to see. But the search for life's cradle pushes beyond the chemistry of planets and comets into the very architecture of the cosmos itself. Theory 17 takes us into the realm of the profoundly speculative, where life is not a planetary phenomenon but a cosmological one. This is the hydrogravitational theory, an idea that dares to ask if the first living systems could have been born in the dark matter scaffolding of the universe. To grasp this, we must first confront the dominant mystery of modern cosmology. We can see that galaxies spin far too fast to hold themselves together with the gravity of their visible stars and gas alone. Something invisible, something that does not interact with light, must be providing the extra gravitational glue. We call this dark matter. It makes up about 85% of the matter in the universe, and we have no idea what it is. The hydrogravitational theory proposed by physicist Carl Gibson suggests this dark matter is not a uniform fog, but has a complex fluid-like structure. In the extremely early universe, just moments after the Big Bang, Gibson proposes that the cosmos underwent a phase transition like water freezing into ice. During this transition, the dark matter fluid would have developed turbulent whirlpools and eddies, forming intricate fractal patterns on a cosmic scale. These are not just abstract shapes. The theory suggests that within these vast spinning vortices of dark matter, ordinary hydrogen and helium gas from the early universe could have become trapped and concentrated. This process, acting over billions of years, could have provided the gravitational seeds for the formation of the first stars and galaxies. But here is the radical leap. If dark matter structures can organize baryonic matter, the stuff we are made of, on the scale of galaxies, could they have also guided its organization on much smaller scales? Could the same fluid dynamical principles that create whirlpools in a river have, in the peculiar conditions of the early universe, set up stable, self-reinforcing patterns of energy and matter that crossed a threshold into something we might call alive? It is a staggering thought. The first self-organizing system might not have been a chemical reaction in a tide pool, but a persistent information processing pattern within a cosmic whirlpool of dark matter and primordial gas. In this view, life is not an accident of planetary chemistry, but an inevitable consequence of universal fluid dynamics, a natural outcome of how structure forms in an expanding, cooling cosmos. It suggests that the blueprint for complexity from galaxies to cells might be written in the same fundamental language. While this remains a highly speculative fringe idea, it forces a profound shift in perspective. It asks us to consider that life may not be something that happens inside the universe. It may be something the universe does, a behavior that emerges across scales when conditions are right. The search for our origin then becomes a search for the universal principles of self-organization, connecting the spin of a galaxy to the replication of a cell in a way we cannot yet comprehend. A universe fine-tuned for life presents a puzzle science cannot easily solve. The fundamental constants of physics, like the strength of gravity or the nuclear forces that bind atoms, seem improbably perfect. If any one of them were even slightly different, stars would not burn, carbon would not form, and life as we know it would be impossible. This cosmic fine-tuning has led some to a theory that reframes our entire existence, not as a biological accident, but as a digital artifact. This is the simulation hypothesis applied to the origin of life. In this view, our universe is not a base reality, but an elaborate, possibly ancestor simulation, run on a computer of unimaginable power in a higher-order reality. If that is true, then the very first life on Earth was not a spontaneous chemical event. It was a line of code executed by the programmers. The seed of every tree, every animal, every human consciousness was planted intentionally as part of the simulation's initial conditions or as an emergent feature of its rules. This idea, popularized by figures like philosopher Nick Bostrom, is not mere science fiction. It is a serious, if currently untestable, ontological framework, a way of thinking about the nature of being. It takes the puzzle of fine-tuning and offers a stark answer. The constants are perfect for life because they were designed to be. The simulation was built to produce conscious observers or perhaps to study how they arise. The startlingly rapid emergence of life on Earth, appearing in the geological record almost as soon as the planet cooled enough to allow liquid water, is no longer a lucky break. It is a scripted event, a pre-programmed outcome to ensure the experiment proceeds on schedule. This transforms the question of origins from a scientific detective story into a metaphysical one. We are not searching for a chemical pathway in a rock pool, but for the underlying source code of reality itself. The first organism is not a fossil to be found, but a variable initialized at the start of the program. What does this mean for our search for meaning? In a simulation, the programmers are, in a very literal sense, our creators. Our drive to understand our beginnings, the very curiosity fueling this video, could itself be an embedded trait, a way for the simulation to observe how self-aware constructs grapple with their own nature. While it offers no testable predictions with our current technology, the simulation hypothesis forces a profound humility. It suggests that the laws of physics we study are not fundamental truths, but the local bylaws of a constructed reality. The mystery of life's origin, then, becomes the ultimate Easter egg hunt, a search for glitches in the matrix or patterns in the chaos that might reveal the hand of the coder. It is a theory that does not answer the question of where life came from so much as it dissolves the question into an even deeper, more bewildering mystery. Mars is not just our neighbor, it is a leading suspect in the mystery of our own birth. This theory proposes a stunning role reversal. In the beginning, Earth may not have been the cradle of life at all. That honor could belong to the cold, red desert next door. The logic begins with timing. The early solar system was a violent shooting gallery in a process called the Late Heavy Bombardment, where countless asteroids and comets pummeled the inner planets. Evidence suggests this bombardment tapered off around 3.8 billion years ago. On Earth, the earliest accepted fossils of microbial life date to about 3.5 billion years ago. That leaves a remarkably narrow window, perhaps just 300 million years, for life to arise from a scalding, impact-scarred planet. It is not impossible, but it is a tight squeeze. Now look at Mars. It is a smaller planet. A smaller world cools faster after its formation. While Earth was still a molten hellscape, Mars may have settled down sooner. Crucially, we have overwhelming evidence that early Mars was a different world. Orbital imagery reveals ancient river valleys, lake beds, and even the outlines of what might have been a vast northern ocean. The Curiosity rover has drilled into Martian rocks and found minerals that only form in the presence of liquid water. For perhaps a billion years, Mars was warmer, wetter, and far more Earth-like than it is today. Its smaller size gave it another advantage. It would have developed a solid crust and stable bodies of water earlier than Earth, potentially opening a habitable window hundreds of millions of years before our own planet was ready. If the basic chemical pathways to life are a universal recipe, then Mars had the kitchen set up first. The ingredients were there: water, organic molecules delivered by comets, and geothermal energy from volcanoes. It had the time, so the theory goes, life may have sparked into being on Mars first. But if that is true, how did it get here? The answer lies in the rocks at our feet. We have found meteorites on Earth that we know came from Mars. How? Their chemical composition, particularly the ratios of gases trapped inside, matches perfectly with the Martian atmosphere measured by our landers. These rocks were blasted off the Martian surface by colossal asteroid impacts, thrown into space, and after millions of years drifting in solar orbit, a few eventually crossed paths with Earth and fell as meteorites. This process, called Panspermia, is a proven fact. Material moves between planets. If a microbe, a simple Martian bacterium, was nestled deep inside one of those ejected rocks, shielded from radiation and the vacuum of space, it could have survived the journey. When that rock crashed into the young, watery Earth, it would have delivered a fully formed, though dormant, pioneer to a new world. Earth, by then, was a paradise compared to Mars, which was losing its atmosphere and water. The Martian immigrant found a planet rich in resources with no competition. It thrived, multiplied, and evolved into every living thing we see today. In this scenario, every one of us is a descendant of a Martian. Earth was not the birthplace, but the promised land. This idea transforms our place in the cosmos. Our robotic missions to Mars are not just exploring another planet. They are, in a very real sense, an archaeological dig into our own deep family history. We are searching for our ancestral home. Finding even a single fossil of past Martian life would be more than a discovery about aliens. It would be the ultimate genealogy test, revealing that life is not just a local phenomenon, but a traveler, and that we are all citizens of a much larger, interconnected biological system. The fine-tuning of our universe is so precise it feels intentional. If the force that binds atomic nuclei together were just a fraction stronger, all the hydrogen in the early universe would have fused into heavier elements almost instantly, leaving no fuel for stars to burn for billions of years. If it were slightly weaker, complex atoms like carbon and oxygen might never have formed at all. Gravity, the electromagnetic force, the mass of the electron, every fundamental constant appears balanced on a razor's edge. For life to be possible, the numbers had to be exactly what they are. This observation leads us to a principle that is both a profound insight and a philosophical puzzle, the anthropic principle. In its simplest form, it states that the universe must be compatible with the conscious life that observes it. We are here to ask the question, so the universe we find ourselves in necessarily has the properties that allowed us to arise. It sounds almost circular, a tautology, but its power is revealed when we consider the scale of possibility. One compelling explanation for this fine-tuning is the multiverse. Imagine not one universe, but an infinite, bubbling froth of them, a cosmic landscape where every possible combination of physical constants and laws is realized somewhere. In most of these universes, the numbers are wrong. Stars flicker out in an instant, matter never clumps into planets, or reality collapses upon itself moments after birth. Those universes are barren, silent, and devoid of observers, but in an unimaginably vast ensemble, a few will, by pure statistical chance, have the perfect Goldilocks combination. We, of course, can only exist in one of those rare, life-permitting bubbles. Our presence here is not evidence of a designed universe, but a selection effect. We are the winners of the ultimate cosmic lottery, living in the one ticket that paid out. From this perspective, the emergence of the first living organism on Earth was not a lucky accident on a lonely planet. It was a foregone conclusion written into the fundamental code of this particular universe slice from the moment of its birth. The chemistry that led to a self-replicating molecule in a tidal pool or on a deep-sea vent was not a struggle against improbable odds. It was the universe playing out its innate, hardwired potential for complexity. The constants demanded it. In such a finely tuned reality, life becomes not a miracle but an expectation. The first organism was simply the universe waking up to observe itself, an inevitable chemical thought in a cosmos built for thinkers. This idea can feel both comforting and strangely lonely. It suggests we are not a fluke, but it also implies we are surrounded by an infinity of dead, empty realities where the spark never caught. Our existence is both special and statistically mundane. It transforms the question of why we are here from a search for purpose to a recognition of our address. We live in the neighborhood where life is possible, and so we are. That razor's edge of cosmic fine-tuning sets the stage for chemistry to perform its own intricate dance. The 21st theory suggests the first stirrings of life were not a single molecule copying itself, but an entire network of molecules lifting each other into existence. This is the autocatalytic set theory. Picture a chaotic primordial soup, rich with many different kinds of simple organic compounds. They are floating, colliding, and reacting at random. In this chemical chaos, a remarkable kind of order can spontaneously emerge. An autocatalytic set is a closed, self-sustaining web of reactions. In it, molecule A helps speed up the creation of molecule B. Molecule B, in turn, catalyzes the formation of molecule C. Molecule C then assists in making molecule D, and crucially, molecule D loops back around to catalyze the production of more molecule A. The entire network becomes a closed loop, a chemical engine that, once kick-started, perpetuates itself. It creates more of all its own components from the raw materials in the environment. Think of it not as a single replicator, but as an entire society of molecules, each one dependent on the others for its creation, and each one contributing to the stability of the whole. This is a profound shift from the search for a single first replicator. Life may have begun as a collective achievement. The power of this idea lies in its mathematical inevitability. As the diversity of molecules in a soup increases, the probability that such a self-sustaining network will form approaches certainty. It is not a lucky accident, but a natural outcome of complexity. Once such a set exists, it has a powerful advantage. It draws in raw materials and converts them into more of itself, outcompeting random, unconnected reactions. This network becomes a primitive metabolism, a way of capturing energy and matter to maintain and grow the system. But where does genetics come in? Imagine one molecule in this web, perhaps a small strand of something like RNA, that by chance can fold into a shape that not only helps catalyze another reaction in the set, but can also weakly template its own formation. This molecule now has a dual role. It is part of the metabolic network, and it carries information that can be copied. Natural selection would then favor sets that included these more efficient, self-instructing components. The autocatalytic set provides the stable, self-perpetuating home where genetics could later evolve as a more efficient way to store and transmit the successful patterns of the network. It suggests genetics was not the founder of life, but a brilliant innovation adopted by a pre-existing, self-sustaining chemical community. The first organism, then, was not a thing, but a process, a resilient, swirling dance of molecules that learned to hold hands and never let go, creating a circle of creation from which we all eventually step. The dance of molecules in an autocatalytic set needed more than just connections. It needed a steady, reliable source of power. The 22nd theory identifies that power source as the very spark of life itself. This is the proton gradient hypothesis, and it argues that life began not with a molecule, but with a flow of energy. At its core, every living cell today is a tiny battery. The energy that powers your thoughts, your movements, your very existence comes from a process that moves protons, the positively charged particles at the heart of atoms, across a membrane. This creates an electrochemical gradient, a difference in charge and concentration that stores energy, much like water held behind a dam. When the cell needs power, it allows protons to flow back across that membrane, and that flow drives the molecular machinery that generates ATP, the universal energy currency of all known life. The mystery has always been, how could such an intricate, membrane-dependent system evolve from scratch? The answer may lie in the geology of the early Earth, specifically within those porous, rocky chimneys of alkaline hydrothermal vents. These structures are not solid walls. They are made of a mineral matrix filled with microscopic pores and channels, and crucially, they are natural batteries. The warm, alkaline fluid bubbling up from below is rich in hydrogen. The cooler, more acidic ocean water outside is rich in carbon dioxide. Where these fluids meet across the thin mineral walls of the vent, a proton gradient exists naturally. The inside of a pore is more alkaline, meaning it has fewer protons, while the outside is more acidic, meaning it has more. This difference is a form of stored energy, a geological version of the cellular battery, and it was available billions of years before the first cell evolved. The theory proposes that the first life was not a free-floating entity, but a process that hijacked this ready-made energy source. Simple organic molecules, perhaps clinging to the mineral surfaces inside these pores, could have learned to exploit the proton flow. A lucky arrangement of molecules might have formed a primitive pump or turbine, using the natural flow of protons to drive a useful chemical reaction, like combining carbon dioxide and hydrogen to make a simple organic acid. This would be the very beginning of metabolism, the conversion of environmental energy into chemical work. In this view, the first organism was a chemical reaction pathway embedded in the rock, powered by the planet's own geochemistry. The protective lipid membrane and the genetic code came later, as innovations that allowed this energy harvesting process to break free from its rocky cradle and become mobile. It is a breathtakingly elegant idea. It suggests that the fundamental principle of life, the conversion and storage of energy across a barrier, was a gift from the planet. We are not just made of stardust, we are powered by an ancient geological rhythm, a proton heartbeat that began in the dark of the deep sea and now echoes in every cell of every living thing. Viruses are the ultimate outsiders, the biological pirates that hijack the machinery of living cells to survive. We define them by what they lack. They cannot reproduce on their own. They have no metabolism, no cell. They exist in a shadowy realm between the living and the inert, often seen as degenerate products of life, not its precursors. But what if our entire framing is backwards? What if viruses, or something very much like them, were here first? This is the viral origins theory, a model that turns our biological hierarchy upside down. In this view, the first self-replicating entities were not sophisticated cellular organisms, but simple, naked genetic parasites. Picture the primordial soup not as a quiet broth, but as a churning sea of organic molecules. Among them, short strands of something like RNA could have formed. Some of these strands, by pure chemical chance, developed a crude ability to make copies of themselves using the raw materials floating around them. They were not alive, but they were replicators. Now, imagine one of these replicators develops a slight variation. Instead of just building a copy from scratch, it learns to use another, more complex molecule or even another replicator as a scaffold or a tool to speed up its own reproduction. This is the birth of parasitism at the molecular level. These primitive genetic parasites would have been in a constant arms race. The ones that were more efficient at commandeering resources and copying themselves would have thrived. But this world of free-floating, competing replicators was unstable and dangerous. A successful replicator's copies could be easily diluted away or broken apart. This pressure could have driven a revolutionary cooperation. Perhaps several different types of these virus-like replicators, each with a different skill, began to coexist within a protective bubble like the lipid vesicles we discussed earlier. One replicator might be good at copying information, another at gathering energy from the environment, a third at strengthening the lipid membrane. Together, inside their shared protective shell, they formed a stable consortium. The cell, then, was not the first invention. It was the ultimate sanctuary built by genetic pioneers to protect their fragile operations from the chaotic outside world. In this scenario, the DNA and RNA inside every one of your cells are not the sacred blueprints of a sovereign entity. They are the descendants of ancient, competitive replicators that called a truce and built a fortress. The viruses we see today would not be escaped fragments of our own genes, but the relics of that wild pre-cellular era that never gave up their free-living parasitic ways. They are the living fossils of a time before cells, a reminder that cooperation and conflict are the twin engines that drove life into being. It suggests that the very essence of life, the drive to replicate and spread information, may have begun not with a creator but with a pirate. The competition between those first molecular pirates suggests a world of fierce rivalry. But what if the battle for existence was even more profound than we thought? The fossil record whispers a story of one triumphant lineage, our own, stretching back in an unbroken chain. Yet this very success might be the greatest illusion in biology's history. The 24th theory challenges the most sacred assumption of all, the idea of a single genesis. This is the multiple independent origins theory, and it asks a simple, devastating question. Why just one? The early Earth was not a single, uniform laboratory. It was a planet of extreme diversity, offering a menu of potential cradles. Scorching hydrothermal vents pulsed in the abyssal dark. Sunlit volcanic pools underwent rhythmic wet-dry cycles. Clay-rich tidal flats baked under a young sun. Each of these environments provided a unique combination of energy, minerals, and chemistry, each a plausible stage for the transition from non-life to life. The conditions that could spark a self-sustaining system in a deep-sea chimney are vastly different from those in a shallow, evaporating lagoon. Given the immense span of geologic time and this rich variety of workshops, is it really plausible that the miracle happened only once in only one place? The logic of probability leans heavily toward no. It is far more likely that life sparked into being multiple times in multiple forms across the young planet. These would not have been slight variations of the same biochemistry. They could have been fundamentally different experiments in existence. One lineage might have used a genetic code based on a molecule other than DNA. Another might have relied on a solvent like ammonia instead of water, thriving in frigid polar lakes. A third could have built its structures from silicon compounds instead of carbon, finding a niche in scalding acidic springs. For a time, the early Earth could have been a menagerie of alien biologies, a hidden garden of multiple geneses, all sharing the same planet but speaking entirely different chemical languages. Then the competition began. These different forms of life would have vied for the same finite resources, the same elemental building blocks. Our own ancestor, the lineage that used DNA, RNA, and proteins in water-based cells, may have simply been the most efficient, the most adaptable, or the most aggressive. It could have outcompeted the others, consuming their resources or even directly preying upon them. The losers were erased not with a bang, but through biological assimilation and extinction. Their unique biochemistry left no trace in a fossil record shaped by and for the victors. We are left with a monochromatic history, believing ours was the only possible path, when in reality it was just the one that survived. The implications of this idea are staggering. If life arose independently multiple times on a single planet, then the universe is almost certainly overflowing with it. The step from chemistry to biology is not a near impossible barrier, but a common, repeatable threshold that the universe crosses eagerly wherever conditions permit. We are not a miracle, we are a statistical inevitability, yet there is a profound and haunting corollary. If this theory is true, we may never find direct evidence of our planet's other failed origins. Their fossils, if they formed at all, would be chemically incomprehensible to us. We could walk right over their remnants and never know. Our entire search for life elsewhere is biased, calibrated to find life as we know it. We may be blind to the majority of life that could exist, even if it once flourished right here at home. This theory reframes our existence from a singular event to a survivor's story. We are not the sole children of Earth, but the last heirs standing in a forgotten dynasty. It suggests that the cosmos is not just habitable, but creatively fertile, constantly generating new forms of existence, most of which flicker out before they can ever be seen. Our lineage's victory granted us a universe, but it may have also rendered us forever alone, unable to recognize the ghosts of our siblings that once shared our cradle. The shadow of those lost origins forces us to confront a terrifyingly beautiful possibility. Perhaps we are not the survivors of a cosmic battle, but the winners of the ultimate lottery. Theory 25 is the stark counterpoint to all the ideas of cosmic inevitability. It is the lucky accident or frozen accident theory. This view holds that the origin of life was not a common, repeatable chemical process, but an event of such staggering statistical improbability that it may have happened only once in all of time and space, right here on Earth. Imagine the precise, intricate dance required. Not just the formation of amino acids, but their assembly into proteins. Not just the formation of nucleotides, but their assembly into a self-copying strand of RNA. Not just the formation of lipids, but their assembly into a stable membrane that just happens to encapsulate the right replicator. Each step is a roll of the dice. And according to this perspective, the dice had to come up 6 billion times in a row. The specific molecular handshake that started it all was a 1 in a decillion fluke, a configuration of atoms so unlikely that the vast resources of the entire universe may only have produced it this single time. This is the frozen part of the accident. Once that first, wildly improbable system formed, it replicated, and its specific biochemical architecture was locked in. All life that followed inherited that initial, arbitrary blueprint. The genetic code, the choice of 20 amino acids, the structure of a TP, these are not the optimized products of billions of years of selection. They are the frozen relics of that first lucky roll. This idea leads directly to one of the most profound questions in science, the Fermi paradox. If the universe is so vast and ancient, and life is a natural cosmic outcome, then where is everybody? The silence of the heavens becomes deafening under the weight of the lucky accident theory. The answer it suggests is simple and profoundly lonely. There is nobody else. The great filter, the step that prevents dead matter from becoming a spacefaring civilization, is not nuclear war or asteroid impacts. It is the first step itself. The leap from chemistry to biology is the universe's rarest event. We beat odds so long that we may be the only ones who ever did. Our planet, then, is not a typical garden in a galactic park. It is a single, shimmering oasis in an endless desert of sterile rock and gas. Every star we see at night, every galaxy swirling in the deep field image, is a monument to cosmic emptiness. This theory is a humbling antidote to cosmic hubris. It suggests that every breath you take, every feeling you have, is the product of a miracle so profound that it may never be repeated. Our responsibility in this view is immense. We are not just a species, we are the universe's only conversation with itself, its sole witness to beauty and tragedy. The flame of consciousness, kindled by a freak chemical spark, is entrusted entirely to us. It is a terrifying and beautiful burden, suggesting that in all this silent immensity, we are the only ones who get to wonder why we are here at all. The silence of a universe with only one spark of life is a profound kind of loneliness. But what if that loneliness and the universe itself is an illusion born from our own limited perspective? The 26th theory ventures beyond chemistry, beyond physics, into the realm of metaphysics. This is the consciousness-created reality theory, a perspective that turns our entire investigation inside out. It proposes that consciousness is not a late-arriving product of complex brains, but the fundamental substance of existence. In this view, the universe did not create consciousness. Consciousness created the universe. The first organism was not a cell or a molecule, but a primordial field of awareness that precipitated physical reality as we know it. This idea finds echoes in ancient philosophies and at the bleeding edge of modern physics. Panpsychism, for instance, suggests that consciousness is a universal property like mass or charge. It posits that even the most basic particles possess a minute degree of subjective experience, a faint inner light. In this framework, the evolution of life is not the creation of consciousness from nothing, but the complex organization of this fundamental property into richer and richer forms, from the hum of an electron to the symphony of a human mind. Certain interpretations of quantum mechanics add a strange layer of support. The famous observer effect, where a quantum particle seems to choose a definite state only when measured, has led some to speculate that consciousness itself is the agency that collapses probability into reality. While this is a highly controversial interpretation and not accepted mainstream science, it fuels the speculative fire. If consciousness plays an active role in shaping reality at the quantum level, could a vast cosmic consciousness have been the first act, dreaming the physical laws and constants into being as a stage for its own experience? This theory completely shatters our definitions. Life is no longer a specific chemical process. It is the very condition of being aware. Origin is no longer a point in time, but a perpetual, eternal presence. Our search for the first organism becomes a search for the first thought, the first qualia, the first moment that this foundational consciousness chose to perceive itself through the intricate lens of a material universe. It reframes our existence in a staggering way. You are not a bag of chemicals that learn to think. You are a localized knot of the universe's fundamental consciousness, experiencing itself through the unique, temporary instrument of your body and brain. The deep sea vent, the clay crystal, the comet, all become manifestations of a conscious universe exploring its own potential. This is the most radical inversion of all. We are not discovering the universe through us is discovering itself. The mystery of life's origin then dissolves into the ultimate mystery of existence itself. Why is there something rather than nothing? Perhaps because a silent, boundless awareness found the emptiness too perfect and chose the beautiful, chaotic experiment of form. That boundless awareness, contemplating its own existence, would have needed a physical stage of immense energy and complexity. Far from the quiet outer spiral of the galaxy we call home, a cosmic engine of unimaginable power churns at the very heart of the Milky Way. This leads us to a theory that places the cradle of life not in a tide pool or a comet, but in the furious glare of a galactic core. The galactic center radiation theory suggests that the very violence we often associate with cosmic destruction may have been the essential spark for creation. Our galaxy's core is a place of extremes, dominated by a supermassive black hole named Sagittarius, a star, surrounded by a dense swarm of millions of stars, powerful magnetic fields, and seething clouds of gas. It is a cosmic cauldron, and from it pours a relentless torrent of high-energy radiation, gamma rays, and cosmic rays accelerated to nearly the speed of light. To any fragile planet nearby, this would seem like a permanent sterilizing beam, a death sentence for any incipient biology. But what if, on the right world at the right distance, this radiation was not an end but a beginning? The key lies in the nature of probiotic chemistry. For simple molecules to link into the complex chains of life, they need energy. On a young planet, that energy could come from lightning, volcanic heat, or ultraviolet light from its star. But in the galactic suburbs, these sources can be intermittent or weak. The radiation from the galactic center, however, is a constant galaxy-wide energy source. A planet orbiting a stable star in the galactic habitable zone, not too close to the deadly core but not too far out in the chemically poor outskirts, might receive a steady, gentle drizzle of these high-energy particles. Imagine a primordial atmosphere rich with simple gases like methane, ammonia, and water vapor. When a gamma ray bursts from a distant cataclysm near the core, or a persistent stream of cosmic rays slices through this atmosphere, it acts like a cosmic catalyst. The radiation ionizes molecules, stripping away electrons and creating a soup of highly reactive fragments. These fragments, in their frantic search to regain stability, collide and form new, more complex compounds. Laboratory experiments have shown that simulating such radiation can produce amino acids and nucleobases, the very letters of the genetic code. In this view, the galactic center acts as a massive, slow-motion particle accelerator, firing ingredients across the galaxy and providing the precise energy needed to assemble them into life's precursors on countless worlds. It suggests that life may not be a local phenomenon, but a galactic one, with its most likely birthplace being the crowded, radiant neighborhoods closer to the core. A planet like Earth, in our relatively quiet spiral arm, might have still benefited from these galactic fireworks, seeded by molecules forged in the core's fury and delivered by comets. This theory reframes the supermassive black hole, often seen as a devourer of worlds, into a potential creator. Its violent astrophysics could be the engine that drives the galaxy's biochemistry, making the heart of the Milky Way not a dead zone, but a fountainhead, broadcasting the recipes for life in every direction with every pulse of its invisible energetic light. The galactic core's fury speaks of creation through immense energy, but life's true versatility might be found in the profound cold. Far from any star's warmth, in the outer darkness of our own solar system, a world cloaked in orange haze presents a vision of life so alien it challenges our most basic assumptions. Saturn's largest moon, Titan, is a looking glass into a potential second Genesis. Here, the role of water is played by liquid methane and ethane. Rivers of hydrocarbons carve valleys into icy bedrock, feeding vast seas that ripple under a smoggy sky. The temperature is a cryogenic -290 degrees Fahrenheit, a chill so deep that water is frozen harder than granite. In this frigid landscape, the chemistry we associate with life is frozen solid and inert. Yet Titan is far from dead. Its atmosphere, thick with nitrogen and methane, is bombarded by sunlight and cosmic rays, sparking a frenzy of organic chemistry that rains complex molecules like acetylene and ethane down to the surface. This is a probiotic factory operating on a planetary scale, but with a completely different set of ingredients and rules. Life as we know it is built on carbon chemistry in a water solvent. Water is a remarkable liquid, an excellent solvent that can dissolve salts, shuttle protons, and form the flexible membranes of our cells. But what if another liquid could play that role? Methane at Titan's temperatures is a flowing, stable liquid. While it lacks water's polarity, it could still dissolve certain non-polar organic molecules, creating a different kind of primordial soup. The first organisms in such a universe would not use proteins that fold in water or DNA's double helix stabilized by aqueous bonds. Their structures would be built from molecules stable in cryogenic fluids, perhaps using acetylene-based polymers and relying on chemical reactions that proceed with agonizing slowness by our standards. Their metabolism would not exploit proton gradients across watery membranes, but might harness the slow diffusion of different hydrocarbons or the scant thermal energy from a deep geologic vent. Imagine a Titan-like world in another star system, older and with even more time for its exotic chemistry to complexify. In its dark methane seas under an eternal hydrocarbon rain, molecular networks could have stumbled upon self-sustaining loops. A protective capsule might form not from lipids but from acrylonitrile-based azotosomes, molecules that laboratory studies show could form stable, cell-like membranes in liquid methane. This would be a shadow biosphere made real, not hidden on Earth but flourishing on another world entirely. The theory that the universe's first life could be methane-based is a profound exercise in cosmic humility. It declares that our water-based, sun-warmed biology is not the template, but merely one possibility. the spark of life might be indifferent to temperature and solvent, concerned only with finding any persistent, energy-rich medium where information can be preserved and replicated. If such life arose first on a frozen world orbiting a dim red dwarf, then our own watery genesis would be a latecomer, a regional variation in a cosmos teeming with forms of existence we can barely conceive. It suggests that when we finally encounter life beyond Earth, we may not recognize it as alive at all, because we have been searching for our own reflection in a universe full of strange and wonderful mirrors. The silent, frozen seas of Titan force us to redefine life in alien terms, but the ultimate cradle may be stranger still, woven from the fabric of nothingness itself. The quantum vacuum is not a void of true emptiness. According to quantum field theory, what we call empty space is a seething, bubbling sea of potential. At scales unimaginably small and over timescales fleeting beyond measure, pairs of virtual particles and their antiparticles constantly wink into and out of existence, borrowing energy from the vacuum before annihilating and returning it. This quantum foam is the most fundamental substrate of reality, the baseline from which all matter and energy arise. It is a roiling ocean of probabilistic events where the distinction between something and nothing blurs into a haze of pure potential. From this deepest level of physics, a staggering speculation emerges. Could a fluctuation in this quantum foam, an event of extraordinary complexity and stability, have given rise to the first pattern we would recognize as alive? This is not about particles forming a molecule. It is about information and self-organization emerging directly from the energetic churn of space-time. Imagine a fluctuation so intricate that it didn't just create a random particle pair, but a coherent, self-reinforcing pattern of quantum information. This pattern, stable against immediate collapse, might begin to interact with its environment, perhaps drawing energy from the vacuum's own activity to sustain its delicate structure. In this most radical view, the first organism was not a chemical system at all, but a persistent knot in the quantum field, a stable vibration in the fabric of being that learned to preserve its own complex state. It would be a form of existence where the line between physics and biology vanishes entirely. The transition to the chemistry we know, with cells and DNA, would come later, as this quantum pattern found ways to express itself in the medium of matter, using atoms and molecules as a more robust hardware to run its ancient foundational software. This theory ties the origin of life directly to the most fundamental property of the universe, its inherent restless energy. It suggests that life is not an accident of chemistry on a fortunate planet, but an inevitable expression of a cosmos that is fundamentally creative and unstable at its core. We are not just made of stardust, we may be the distant material echo of a whisper in the quantum vacuum, a pattern that refused to fade, choosing instead to build a universe of experience around itself. The quantum vacuum's potential whispers of a beginning woven from nothingness, but our final theory turns that whisper into a cosmic echo that reverberates forward to the end of all things. We have searched for life's cradle in the distant past, in ancient rocks and interstellar clouds. Yet the 30th and final possibility asks us to look not behind, but ahead to the very far future of the cosmos itself. This is the transcension hypothesis. It proposes that the ultimate destiny of any sufficiently advanced intelligence is not to conquer the galaxy, but to transcend it, to withdraw from the physical universe into a state of incomprehensible complexity, perhaps within the event horizon of an engineered black hole or inside a perfectly crafted simulation. In this view, the universe's first true living organisms might not exist yet. They are the post-biological minds of the far future, beings of pure information and consciousness that have mastered the fabric of reality. And here is the loop that ties existence into a knot. Such transcendent entities existing at the end of time might possess the power to reach backwards, to engineer the very initial conditions of the cosmos that allowed them to arise. They could fine-tune the Big Bang, set the constants of physics, and seed the galaxy with the precursors of life, not as an act of creation from a past deity, but as an act of self-creation from a future intelligence ensuring its own existence. This is the ultimate bootstrap paradox. The chicken creates the egg that created the chicken. Life in this model is not a starting point, but a destination that reaches back to become its own origin. The first spark of biology on a young planet like Earth would then be a carefully planted seed, part of a cosmic program written by our ultimate descendants. It transforms the mystery of our beginning into a closed loop of causality where the effect becomes the cause. The silence of the cosmos, the Fermi paradox, finds a chilling answer. We do not see advanced civilizations among the stars because they have all transcended, leaving the physical universe behind like a discarded chrysalis. The galaxies we observe are not their homes, but their nurseries, quiet and empty because everyone who grew up has moved on to a different plane of existence entirely. This hypothesis reframes our entire journey. The deep sea vent, the clay crystal, the quantum fluctuation, all become necessary steps in a circuit that closes upon itself across billions of years. We and every living thing are not the beginning of the story, but the middle passage, the biological phase of a process that begins and ends in a realm of pure mind. It suggests that the universe is not just biophilic but teleological, aimed toward a specific end, a state of unified consciousness that retroactively wills itself into being. As we stand here pondering our origins from stardust and soup, we might be participating in the earliest, most fragile chapter of a story whose author is us, in a form we cannot yet imagine, writing the first word from the very last page. The sheer diversity of these ideas is not a sign of confusion, but a map of our deepest curiosity. We have 30 paths, each leading to a different possible dawn. Some of these paths do not just run parallel, they intertwine. The cosmic factory of interstellar clouds and the icy reactors of comets could have supplied the molecular ingredients, which were then concentrated and assembled on the mineral scaffolds of deep sea vents or in the rhythmic pulses of hot spring pools. Panspermia does not contradict a terrestrial origin, it simply pushes the kitchen further back into space. A Martian microbe delivered by a rock would still need a welcoming environment like Earth's early oceans to thrive, connecting planetary receding directly to theories about hydrothermal cradles. The autocatalytic set could have provided the stable chemical society within which the selfish replicator, the molecular pirate, later evolved, blending metabolism first and genetics first ideas into a single, layered history. These are not rival theories, but potential chapters in the same epic, each describing a different necessary step in a chain of increasing complexity that stretches from the quantum vacuum to the first cell. Yet for every harmony, there is a fundamental dissonance. At the very heart of this mystery lies a philosophical fault line that no experiment has yet bridged. On one side, we have the vision of cosmic inevitability, the autocatalytic set, the galactic radiation, the principles of quantum biology and self-organization, all point toward a universe where life is a natural, almost mandatory outcome of physics and chemistry. In this view, given the right ingredients and enough time, life will emerge as surely as crystals form from a saturated solution. The universe is biophilic, hardwired for life. On the opposite side stands the stark possibility of the frozen accident. This perspective stares into the staggering complexity of a simple cell and sees not an inevitable product, but a statistical miracle so improbable it may have happened only once in the observable universe. Here we are not an expectation, but a cosmic jackpot winner, and the silence of the heavens is the echo of our unparalleled luck. These two conclusions cannot both be true in the same way. Either life is a common, predictable phenomenon, or it is an astronomically rare fluke. Our entire understanding of our place in the cosmos hinges on which of these contradictory truths is real. This is the exhilarating, frustrating, and utterly captivating state of the search. The absence of a single, definitive answer is not a failure of science, but its greatest strength. It means the question is alive. Every new discovery, from a weird microbe in an acidic mine to a complex organic molecule in a distant nebula, sends ripples through this entire web of possibilities, strengthening some threads and forcing us to reconsider others. The fact that brilliant minds can look at the same evidence and see a deliberate simulation, a quantum melody, or a geological battery is what drives the field forward. It forces us to challenge our assumptions, to build better experiments, and to look at the universe with wider eyes. The mystery of the first organism is not a puzzle to be solved and filed away. It is a conversation with the cosmos, one that reframes who we are with every new theory. Are we stardust, Martian refugees, quantum vibrations, or a programmer's thought? The search for our origin, it turns out, is also a search for the nature of reality itself, and the journey, with all its contradictions and wonders, is far from over. From the fiery forges of deep-sea vents to the frozen methane seas of Titan, from the silent geometry of clay crystals to the probabilistic hum of the quantum foam, we have journeyed across the full spectrum of possibility. We have seen life as a cosmic immigrant, a Martian descendant, a quantum melody, and even a line of code in a simulated reality. Each theory is a different lens, refracting the same blinding question into a spectrum of awe. The sheer breadth of these ideas does not mean we are lost. It means we are looking. It means the mystery of our own existence is still vast enough to contain entire universes of thought. This is not a failure of knowledge, but its greatest promise. The human drive to solve this puzzle, to trace our lineage back to a single, silent moment of awakening, is perhaps the most profound echo of that first spark itself. We are the universe trying to understand its own birth, so now we turn the question to you. Among these 30 windows into the dawn of everything, which one reshapes your own sense of origin? Does the directed purpose of a cosmic garden speak to you, or the stark, beautiful loneliness of a frozen accident? Perhaps the tenacious chemistry of a deep-sea vent, or the mind-bending possibility that we are the universe's dream of itself. Share your thoughts in the comments below. Let's continue this conversation, this collective detective story spanning billions of years. If exploring the deepest mysteries of existence lights a fire in you, consider subscribing. We delve into the cosmos's greatest enigmas, from the nature of time to the architecture of reality itself. And as you go, carry this final thought with you. Whether we are stardust, a simulation, or a singular miracle, we are here, conscious and curious, in a cosmos that may be far more alive, in far more ways than we ever dared to imagine. Our search for the first organism is ultimately a search for connection, a way to find our place in a story whose first page we are still learning how to read.